Alright, let's get started with some of the information you'll need to be successful in weeks 4 and 7. This is our pumps, 3D drawing and printing, and energy efficiency segment of our course. This is going to be divided up because of our opportunity to use our 3D printing resources to make parts that we'll need for week 7. So we're moving into beginning of a long-term project that will explore, assemble, and test a water treatment system that controls salinity and temperature. This is a working kind of fish tank model that has characteristics that are similar to other systems across different disciplines. Examples would include water treatment systems in civil engineering, medical applications for on-the-body treatment systems, chemical manufacturing processes and control systems, and also other applications in manufacturing. We'll take this work and explore mechanical engineering elements of the system. The pumping of water is a cross-disciplinary idea. The design of pumps to efficiently move water combines the application of an electrical motor to the drive of the pumps. Our class experiences will include learning about using calipers for measurements, applying those measurements to 3D design of pump parts, learning how to take electrical measurements and to measure energy and power, and then collecting data on pump characteristics for efficiency and flow rate versus head height, and we'll talk more about that later. So let's overview our system essentially. So this is a simple sketch for it. Imagine our saltwater fish tank, and it's going to have a recirculating pump. So the pump is going to take in the water in the lower section here and recirculate it around, and we'll be managing the temperature of the tank and the salinity of that tank. So the pump is being driven by the motor, and so this is the piece we're going to focus on today. But there are some other systems that we'll be adding later on in the term. We'll be looking at the electrical circuits that discuss cascaded switching and the power needs of the system. We'll be looking at heating and cooling the water, both the temperature sensing and then the temperature control. Next, mass balancing of the water, salinity. So salinity sensing and salinity control are the next element. And finally, controlling that system by reviewing the sensitivity of the sensors, how accurate they can be, and implementing a programming control method within a Lego RCX microcontroller, taking inputs and outputs and making decisions with that. First, let's take a look at a few pump types. I picked a couple of historical pumps and then the pump that we'll actually be using for our work. So the historical one, the first one that I like is this rope pump. And of course, it's a hand-cranked pump. Looks like a bicycle wheel as the rotating piece. We've got a rope loop, and on that rope loop are several rubber pistons or valves that are suitable for sliding up into a tube that reaches from the surface down into the tank of water. And so let's describe how this works quickly. So as the system rotates counterclockwise here, the pistons travel underneath the water and begin to enter the rise pipe. So as they enter the rise pipe, they carry with them, as they trap water above them, they carry water in between each of the piston valves. Alright, so as that water is carried up by the person cranking, when it reaches the top, it vents and the water drains off through the spill pipe into the bucket. So you can actually get very consistent flow with this. Of course, it has to have someone working it. I've actually built a small version of this, and I was surprised how much water it can move. So the second example is also unique. It's an impulse pump. So this impulse pump takes advantage of the difference in height between one water source, say a river on an upstream side, and another water source on the downstream side. So that potential difference in height allows this pump to operate, along with one of the characteristics of turbulent water flow. So as the water drops down this first part into this well, it takes advantage of this inverted geometry down here at the bottom. So the turbulent water flow carries air with it. The air gets trapped in this inverted section and begins to fill up. And as it fills up, of course, it pushes the water down. Now the rise pipe, as the air reaches the bottom of the rise pipe, it will vent and allow air to exit out. But as the air exits out, the water inside rises up again and seals off. So you end up having alternating water and air going up the riser. And so this pulsar pump pulses due to the fact that air is filling up, venting, and filling up again. So it is actually able to move water much higher than the change in energy that they've got normally. And so this pulsar pump is a very unique situation. The final pump we're talking about is the centrifugal pump. So this is what we'll be working with. It has inside the housing, or the volute they call it, is a spinning impeller. That impeller adds velocity to the water, and that velocity causes the water to, of course, exit the discharge side. Water is sucked in through the face, thrown out by the impeller, and then exits through the discharge line. This is a time pump that we'll be working with, and I'll show you a few examples of the impellers here in just a second. So let's take a look at impeller designs real quick. So a centrifugal pump design has three key areas: impeller design, volute or housing design, and then designing for friction or reducing friction actually. So looking at the impeller itself in either one of these screens, these samples, as the impeller spins, its rotating speed controls how much work it does. Its diameter and the shape of the vanes are the things that you would control. So the volute, on the other hand, is the size and shape here, and so it has two key areas that we think about. As the impeller spins, it's going to bring the water around, and as the water comes near the exit, it's going to go out through the throat. So the size and shape of the throat controls the velocity at some level, and then also how close the tongue identified here is to the impeller is another area of design for the pump. Of course, all of this, they're looking to reduce frictional losses so that the pumps can operate very efficiently. This image shares a few examples of impellers. Most of them are for centrifugal pumps. Some of them are certainly more complicated than we'll need for our purposes of testing a simple pump. These are type of almost squirrel cage, so they've got a flat plate with a fin sticking up, and so you'll be drawing something most like the one on the inside. These images might make more sense if you consider where the water is coming from. So we want water, in this case, comes in through the face and gets exited out the sides. All right, particularly for our first week of work, we'll be doing measurements and drawing in preparation for other work. The vernier calipers that we're going to be using in class are a good example. So I strongly recommend that you go out to this website, mdmetric.com, and check out this vernier caliper example. It's a great example of how to use them. This particular example shown on the screen shows 11.7 millimeters being read, and so you can identify that here by marking the 11th tick mark. This 0 on the lower jaw is past the 11th tick mark, and it looks like it's about over 70 or 80% passed from the 11th tick mark to the 12th. Now with that information, you scan down to the lower jaw and look at its tick marks, and you'll notice that the 7 is marked here, but it lines up perfectly with the one right above it, and so that's how we're able to select it. If you look at the 0, the 1, 2, 3, these tick marks do not line up with the line that's just above them. Their spacing is designed such that when they line up, that's the digit you'll use. So this is reading 11.7 millimeters. A good example, so go out and give it a try. It should work out very well. Alright, so again, those measurements will be used to complete our drawings. Whether you're using SketchUp as we suggest for new folks, or you're a more experienced drafter and you have some another program you want to use. We'll be taking measurements of this pump assembly, in particular taking the measurements for the housing, the impeller, and then the cover here. So we'll be practicing this in class, and the team will be selecting the best 3 impeller drawing to have printed at the beginning of the robot programming lecture. So this is what we'll be working on, so make sure and practice with SketchUp or your program before class. There's been a few videos posted on this, so make sure and go out there and take a look. Alright, some students have had a chance to work with 3D printing. We've inserted the programming section of the class in between the 2 weeks involved for the motor and pump section. This will allow us time to actually get parts printed that the teams will design. So our system is a Stratasys printer. It's a U-print system that has approximately 6 by 8 by 6 volume that we can build in. The great things about rapid prototyping and 3D printing is they give you the chance to move your ideas along faster. In many cases, they'll allow you to functionally test a part, and in our case, we'll actually be able to use it for what we're doing with our pumps. The final design support can also be very good. The models can be used to repair molds or other production materials so that you can move from a low volume to a high volume. 3D printing is a good example, excellent example of additive manufacturing. Rather than removing parts through machining, you're laying down only the material you use. And it's developing increased use as a full production system. So there are a handful of printers. Of course, I said we had the Stratasys printer. There's also some lower-end maker-bought products, and 3D Systems, another high-end system. So we'll get you a little experience with these. Again, make sure and go out and watch a couple of 3D videos about printing. We'll see if we can't take an image of one of our prints in the next couple of weeks.